insulated rigid tank contains 4 kg of argon gas at 450 kilopascals and 30 degrees Celsius. A valve is now opened and argon is allowed to escape until the pressure inside drops to 200 kilopascals. Assuming the argon remaining inside the tank has undergone a reversible adiabatic process, determine the final mass in the tank. So based on our problem, an insulated rigid tank contains argon gas at a specified pressure and temperature. A valve is opened and argon escapes until the pressure drops to a specified value. The final mass in the tank is to be determined. So before we will start in solving our problem, we must identify the given first. So we have 4 kg as the mass of our argon gas, 450 kilopascals as our initial pressure, 30 degrees Celsius as the initial temperature, and 200 kilopascal as our final pressure. So let's assume at specified conditions, argon can be treated as an ideal gas. So the process is given to be reversible and adiabatic and thus isentropic. Therefore, isentropic relations of ideal gases apply. So from the ideal gas isentropic relations, we have here the equation. The final temperature is equal to the initial temperature multiplied by the quantity of the final pressure over the initial pressure raised to K minus 1 over K. So we must first find the final temperature in order to solve for our final mass in the tank. So we have here the K as our specific heat ratio and it is unknown. So we can determine this K from our property table, which is from table A2, which is for argon, which have the specific heat ratio of 1.667. So since the given values is sufficient into our equation, we can now plug in the given values in this equation. So the final temperature is equal to the initial temperature, which we have 30 plus 273 Kelvin, since we must express our temperature in Kelvin, multiplied by the quantity of the final pressure over the initial pressure, and we have now 200 kilopascals over the 450 kilopascals, which is raised to 1.667, which is the specific heat ratio minus 1 all over 1.667. So plugging in these values in the calculator, we will now have our final temperature, which is 219 Kelvin. At this time, we can now proceed in solving the final mass in the tank. So the final mass in the tank is determined from the ideal gas relation. So we will use this equation. The initial pressure multiplied by the volume all over the final pressure multiplied by the is equal to the initial mass multiplied by the gas constant R multiplied by the initial temperature all over the final mass multiplied by the gas constant R multiplied by the final temperature. Since volume and the gas constant here is both common, we can cancel this volume and gas constant. So we will now have the initial pressure over the final pressure is equal to the initial mass multiplied by the initial temperature all over the final mass multiplied by the final temperature. So we will cross multiply this equation and we will now have the initial pressure multiplied by the final mass multiplied by the final temperature is equal to the final pressure multiplied by the initial mass multiplied by the initial temperature. So from this equation, since we are finding the final mass of our argon gas in the tank, we will now divide both sides of this equation with pressure 1 and the final temperature. So we will now have the final mass equation, which is equal to pressure 2 multiplied by the initial mass multiplied by the initial temperature all over the initial pressure multiplied by the final temperature. So plugging in the values in this equation, we will now have 200 kilopascals multiplied by 4 kilogram multiplied by the temperature, which is 30 plus 273 Kelvin all over 450 kilopascals multiplied by 219 Kelvin. Plugging these values in calculator, this will result to the final mass, which is equal to 2.46 kilogram.